Welcome everybody to Happy Maths Hour with Toni, the lovely Toni Beardon, and myself with my crazy hat today because I'm doing a little bit of performing. And today is all about paper sticks and what we can do with paper sticks. I've been rather busy beavering, making lots of paper sticks, and Toni's written some lovely, well, some of these resources are actually my ideas, which is rather special. But Toni's made some fantastic resources around them. Over to you, Toni.
Well, hello, everybody. Yes, we're really excited to be sharing our paper sticks with you. You see, Caroline's a wonderful entertainer, and she does entertainment with balloons and bubbles. But the balloons, okay, it's maths with balloons, and maths with balloons is fantastic. But what can the teachers do in the classroom? I mean, balloons are not exactly classroom friendly. And so what we invented between us, and it was like, it was one of those aha moments, wasn't it, Caroline? Because we were trying to think of a way to make it possible for teachers to do the same activities with the children in the classroom. And so all the activities that Caroline does in her maths show can be done with these paper sticks. So here are a few of them. Okay.
Right. Ready.
And
here goes.
You've got to make your paper sticks first.
You do. And we're doing this the old-fashioned way, the new-fashioned way, the different way. Oh, right. That is, right. I know what I've got to do. This one. So here we go. We've got to make the paper sticks first. So what we're going to do is we're simply going to play a video for you, which is on YouTube, and it's on the MathsToys YouTube channel, which is in the link. Go ahead and click on that when you want to. There's about 8 videos related to paper sticks.
Hello, I'm Toni from AIMSSEC, and I'm going to show you how to make paper sticks. Now, you may ask, why paper sticks? Well, we've got lots of uses for them. We've got some puzzles, you can make models, and also you can make sticks of different lengths. You can even make a metre-long stick and measure heights or the width and length of a room. The one I'm going to show you today is just made with ordinary scrap paper, A4, and the other things you'll need are some sellotape, some scissors and some string. Now we'll just fold the piece of paper in half and cut it to make our paper stick, and I've just got this one which I'm going to use now. Now I'm going to fold the strip of paper in 3. It doesn't have to be absolutely exact, near enough in 3. Then I'm going to tape my piece of string in the middle, and the reason for doing this is that if I do that, just secure it there, it won't pull out later on when I've made the stick. Now, we just roll it as tightly as we possibly can. Keep rolling and keep it as tight as you can. You can always start again if it comes loose. There we go. That's all it needs now is to be secured, and we found the best thing to do is to make the sellotape go all the way around so that it will stop it coming unrolled. Yeah. On the MathsToys YouTube channel, you'll find ideas for using these sticks. You'll find puzzles. You'll find ways to make models, and you'll find other lesson ideas. And we hope you'll enjoy them. Subscribe and comment. We want to know how you like our puzzles and games.
Brilliant, Toni. We had fun making that, didn't we?
We did, some time ago, before COVID, actually.
It was just before COVID, wasn't it?
I don't think I've had my hair cut since then.
No, I haven't either. Mine's quite long now.
Okay, so one of the things I talked about in that video was making a meter stick. And, well, Caroline is going to show you, but yes, she's got one there. And she's used white paper, but you perhaps don't have...
I don't have newspaper.
No.
And I can't go, well, I'm not going to go out and buy a newspaper, especially. You can see in the photo, you use whatever paper you had. Now, I had this, I've used the flip chart paper. Used flip chart paper is great for this. And I've got another stick back there that I'm made with used flip chart paper. So we encourage, obviously, using and reusing. I mean, you could even use a long piece of cardboard, couldn't you, Toni? If you had a box that was 1 meter long, so you roll it up.
It'd be really hard to roll the cardboard, but I think your paper's better than the newspaper in the sense that it's stiffer. But newspaper's perfectly fine, and most people can. Well, Caroline, my dear, you could go to your local news agent and say, "Can I have some of yesterday's newspapers?" And if they haven't been collected and shipped away somewhere, anyway, why a meter length? Well,
believe it or not, Toni, there isn't a local news agent. I have to go some distance. I'd have to go about a mile, and I'm not going out.
I'm going to give you some newspapers next time I see you.
Oh.
Okay, so why a meter stick? Well, you can buy a meter stick, but they're quite expensive, and a homemade one is just as good. And if you're working with a lot of children, every child or every pair of children can have their own.
I have a dream. Brilliant. I have a dream where the teacher says, "Everyone pick up your meter stick." Everyone's got one.
Yes. Well, they're rather big, so maybe they do need to be stored somewhere.
Yeah, they have to be all together in a bucket in the back, and everyone can write their name on it.
They could indeed. So they could make them in pairs, and you just do it in exactly the same way as I just showed you on that video. But here now, you need to make your paper 1 meter long. And that's why you see there's a tape measure in that picture, if you look closely. And it is exactly 1 meter long. And of course, it can be just a little bit more than 1 meter and trimmed, if you like. And then it's rolled tightly. And then you get a ruler. We'll use that long tape and mark 10 centimeter lengths along the meter stick, and you're ready to go. And of course, you could take one of the 10 centimeter lengths and mark it into centimeters. And there's lots of activities. I mean, you will find as a teacher or at home many activities. First of all, how good are you at judging lengths and distances? Are you good at judging lengths and distances, Caroline?
I have actually had a lot of experience. I've done a lot of work on building houses. So I actually am pretty good at judging both meter lengths and the smaller lengths as well. So Caroline does this
wonderful show, and sometimes she's got hundreds of people in the auditorium. And she asks the children how many meters across, how many meters from back to front in this room, in this auditorium. And everybody has to estimate. And then she gets her meter length balloons and gives one to each child and gets them lined up. And so the balloons are end to end, and they go from one end of the room to the other. And then everybody counts. And when you get about halfway, Caroline, you say to people, "Do you want to change your estimate?"
I'll get them to be revising their estimate.
Yes.
You used an expression the other day, which was better than it was a really nice expression you used.
What, guesstimate?
No, it wasn't guesstimate. It was about what I say is you revise your estimate and then you make a better guess. But you came up with a better expression than that.
I don't remember exactly, but it might have been trial and improvement.
It wasn't that, but that's good. But it wasn't that. It was best. I don't think I wrote it down, which was silly of me. But yes, no. But that's the idea that you're not expected to know it. I mean, especially if you don't know. Like if you're 10 and you really don't you're starting to get an idea of how long a meter is. It's very hard to estimate the length of a room. I had a group of 14-year-olds the other day, and some made some great estimates at that side of the hall we were in, because we were in a big hall because of COVID, but some way out. Why? Because they didn't have the experience, and this is how you gain the experience. Absolutely. By doing activities like this, and that's how you get good at it.
Absolutely. And when you start to learn to drive, it's really an important skill, because you're given in the highway code, it says about being able to see a number plate at a certain distance, and keeping your distance from the car in front, and so on. So these sort of it's distances and also fairly short lengths. So measuring heights, for example, can you estimate the heights of people? And more than that, one of the things that a class often does is to measure everybody's height and to record the heights. And this is an exercise in collecting information and data for some sort of statistical study. But it's really useful to be able to interpret scale on maps and plans. So you're looking, so often we draw a plan of something. It might be a rough plan, or it might be a quite carefully drawn plan. Most people, if they're going to do something in craft work, let's say they're going to make something in maybe in woodwork, or if they're going to they're going to sort of tile a room or a wall. Lots and lots of times you want to be able to make a scale drawing and interpret a scale drawing. And Caroline, you recently had to construct some flat pack furniture, didn't you?
Yes, indeed. And I tell you, when it's useful for that, but it's really useful when you go to IKEA or any furniture shop. I literally use my body. I know what my meter length is. It goes from my shoulder to the end of my thumb when it's actually sticking out that way. I call it a thumbs out meter, or a hitchhiking meter. And I know that's a meter. And I also know my height meter that goes from the floor to basically where my belly button is, more or less. And so I can really easily work out, without getting a tape measure out, to get fairly accurate measurements.
Will it fit? That's a question.
Will it fit?
Yes. I mean, this piece of furniture, will it fit in that place where I have a mind to put it if I buy this piece of furniture? Okay, so lots of reasons for this being a good activity. And you don't need any expensive equipment, and it's great fun for children and adults alike.
And measuring, like your house, measuring around your house, seeing how big your garden is, and just if you want a pool, you say, well, I want a pool, Mum, Dad, and you say, this is how big it needs to be because you've measured it. That might give some weight to the argument of getting a pool if you've measured it, and you never know.
A pool for people to swim in, or a pool for frogs and fish? Absolutely.
And then work out how much water you'll need as well.
Yes. Okay, now Caroline, you're going to show us something about the Tets and Octs puzzle.
I am, and I just remembered that you wanted me to show a picture, which I've just found just in time. Tets and Octs, right? Here we go. Tets and Octs. Well, we're going to start with a balloon. So I'm going to change the. Here we go. So you can see what I'm doing. So I'm going to use a balloon. Now you will be doing this with paper sticks as well, but I'm just going to show you the fun part of doing it with a balloon. Now you can also do it with a balloon, and two people is very useful because you can get one to hold it, and if you twist, you always twist in the same direction, because if you don't, and always hold it or else it pops out. If you twist in the opposite direction, it pops out. You learn a bit of physics while you're at it. and then you kind of work it out as you go. If you and there are videos on the Bubbly Maths YouTube channel that show you how to do this. So just Bubbly Maths on the YouTube, you'll find it. Okay, here we go. We're making this shape. So this is the puzzle. So here is 2 triangles. This is how this puzzle started out. And then I discovered this amazing woman called Vi Hart that also does exact. I don't know if actually she does exact. Excuse me, I'm going to make a noise now. Ooh, uh-oh. Oh, boy. Oh, I might have to reinflate that one. And she does some great puzzles, and she does some of the puzzles that I was already doing. And then, thanks to her, I had more puzzles. I used a lot. The remainder was the puzzles that I hadn't thought of that she does. This one came uninflated, so now I'm going to make another stickety stick. Boing, boing. Right, so the challenge is we've got 2 triangles and we've got 1 extra edge. So we're going to give it some language. All these are all edges, so you might call them sides, but then you can get confused between the side of a building or the corner. So we're going to keep the language very clear. This is an edge. The pointy bits are vertices, or 1 vertex, many vertices, and then we've got 1 extra edge, and the shape of the face, well, this is a 2D shape, so actually it's a rhombus, as you can see on the outside, but the rhombus is made up of 2 triangles. So the challenge is using 1 extra edge, and you can draw this on a piece of paper. 1 extra edge, we need to make 4 triangles, not 2, but 4, and we only have 1 extra edge. We cannot bend the edge in the middle. We can't do anything, no jiggery pokery. In order to join it together, I'm going to make a little bubble at the end. That's to join it somewhere, but we can't actually split any of these edges anywhere other than at the vertices. We can't bend or break or anything, any of these. I'm watching you. So 2 triangles into 4 using 1 extra edge. Now I've done that with balloons, I'm going to get out, I'll solve that with the balloons later. But I'm going to get out the, oh my, where did I put it? It's here. Okay, so we've got the same thing here. But this is made with paper sticks, and we've got 1 extra stick, so we can put it, let me see there. Okay, I've got 2 triangles, and some people might say I've got 4 triangles there, but if you look carefully, whoops, use my front eyes. If you look carefully, the shapes above actually have 4 edges, not 3. And so you might go that way. Again, you've got the same problem. You've got 2 triangles and 4, whoops, so it could be, oh dear, lost a piece of string. You've got 4 edges, not 3, but plus there's other ways that this way as well. So you can put it there, but then we've got the problem that a triangle is a closed 2D shape. So it's 2 dimensions, but it's closed. All the edges are straight and it's got to be closed. So we can actually only make 1 closed triangles on 1 of those vertices. And on the other side, it's open. The only triangle is there. So what can we do? How on earth can we use 1 stick to make 4 triangles when we start with 2 and we only got 1 extra stick? Well, Tony, should we give them a clue?
Well, all the triangles have got to be the same.
All the triangles have to be the same.
Yes.
And I might give you this clue here. That's one of the places where that extra stick is going to fit. And then what we're going to do is we're going to use the magic of 3 dimensions to now make...
Wow, it's a pyramid or tetrahedron. Wonderful.
Yeah. Tetrahedron, which is, okay, so you're now going to learn some ancient Greek. So ancient Greek, so in English, this thing has 1, 2, 3, 4. 4 faces. Well, in ancient Greek, it's called a tetrahedron. So what could tetra mean and what could hedron mean? 4 faces, tetrahedron. So you just learned some ancient Greek. I think you probably put 2 and 2 together and got 4 faces. So good job there. That's one of the puzzles. Now, you've come up with a challenge for the second puzzle, Toni. You seriously want me to start with this? This is where we're starting.
How many sticks have you got there?
We've got 2, 4, 6, 8, 10, and 12. We've got a loop of 12 sticks.
Yes, that's what you can see in the picture.
It's exactly what you can see in the picture, and I can't exactly hold it out because it goes downwards. But if I had 2 more hands, I'd make a square with 3 sticks per edge.
And Caroline,
yes.
Caroline has made hers all sort of loose because she's going to undo it, not now, but later on, and so you can reuse the sticks. But you can tie those knots a little bit tighter, Caroline.
Yeah, this actually, I've used this again and again and again and again, Toni, and that was before you taught me the special new knot. So this has actually been in operation for some time. So I'm reusing and reusing, so that's good. But this one I made today. No, that one I made today. This one I made, but this one I've used a slightly different technique. So I'm going to use this one. And the thing is, we've got a loop of 12 sticks, and we're going to make a shape with 8 equilateral triangles. So with our tetrahedron, they were equilateral, and they were all the same. So this is a platonic shape. Every face is the same shape, more or less. Every edge is the same length, and every vertex has the same number of faces on it. So it's a regular 3D shape.
And you can, if you take time and you arrange it and you tie the knots tightly enough, you can make a pretty good tetrahedron.
You can make a very good tetrahedron. It's just the skeleton of a tetrahedron, of course. It isn't a solid. Just to qualify that one. But if you could wrap it in wrapping paper and Christmas paper or brown paper or newspaper, and then you could make it a solid. Okay, so we've got to do that with this one. Now, how on earth? I've got to make how many? 8 equilateral triangles without breaking the loop. So here's the loop. Now, this is best done with 2, and even better, 3 people. You'll see how many vertices. So I'm going to make, there's one triangle. Okay, good. I've got one triangle. But now the rules, this is also a platonic solid. So the rules are the same in terms of what I said here. Every edge must be the same length. Every vertex must have the same number of edges or the same number of triangles leading off it. And every face must be the same shape. So we know the shape's a triangle, so that's fine. But now I'm going to give you a little bit of a hint. Every vertex must have 4 edges and only 4 edges. And every edge is a unique stick as well. So we're going to use all the sticks, and every stick is going to make an edge. Now, this is the bit where it gets difficult because I've only got 2 hands, but this is why I've attached these. I've attached the cable ties on it. This is a new invention, Toni. Came up with this idea so that we could actually do this. And so you can do it on your own. And I've got to do it. Okay, so now we've got that there. Okay. There. And now that's okay. So there I'm going to, oh, look, I've made another triangle now. By joining those 2 like that, I'm making another triangle. Oh, boy. This is, and you can get yourself in a bit of a muddle, but the great thing with these cable ties is you can untie them as well. Okay, well, I've got one here. I'm going to make another triangle. So I've got 3 triangles going here now, and I'm using it's a much easier, much quicker if you've got more than one person, but I'm just showing you here that even if you're on your own, you can still do this. Now, I've got 4 edges there. but I've only got 3 triangles, so I need to complete. Whoops, it's mirrored. What I'm doing is mirrored, so it's my. Now, how am I going to do that? I've got, well, I haven't got one there that I can complete that with, so I'm going to go and, oh, here we go. I can make a triangle there. So there's one. Oh, and now if I make a triangle there, now I've got the edge to complete that one there, and without. See if I can now just hold these in place and there complete the shape, which one I made earlier is an octahedron.
Wow, Caroline, that is beautiful. And
so let's see, we've got, you can see the symmetry if I do this. There you go.
It's really not something to do on your own. But it's easy.
And it's actually a lot more fun if you do it with somebody else as well. This is one of the workshops that I do, especially with family groups in science fairs and things. And I give them the challenge. They have to go off and come back, and they can see them. Sometimes they'll spend 10, 15 minutes working on it and just really enjoying it and working together as a family. It's beautiful.
And there's lots of other models you can make. Shall we move on, Caroline?
Yes, I'm ready.
That was really...
Oh, let me just finish the balloon one. Here you go, make another, whoopsie, make another bubble there. Kerpow, and there you go.
Okay, I've gone the wrong way. Now, if you've got a loop of paper sticks, can you use it to find different rectangles that have the same perimeter? I mean, you just got your loop, you don't break it, you just make different rectangles, and then we're going to look at some other shapes. So there are 2 rectangles that you can make with the same loop as Caroline just used to make the octahedron. And you can perhaps look and you can see what the areas would be. They've got the same perimeter, 12 units. What are the areas?
And if you want, you can actually make more sticks to actually join the internal one, so that you can see the matrix. Make the grid. Thank you. Yeah. You can do that if you want it, if it helps visualize.
And you can count, but it's 9 and 8, isn't it? Okay. Can you make other rectangles? Can rectangles have the same perimeter in different areas? Clearly they can, because those 2 have both got a perimeter of 12 and an area of, well, different areas. And there are 3 rectangles all having a perimeter of 12 units, but different areas. What about 16 units or 18 units? And then not just rectangles, triangles, other shapes. You don't have to have the sticks. You can just sketch the shapes. So we can now just think of it. But
I'm going to see if I can actually... I'm not sure if I've got enough space here, but I've got one of 18 here, and I'm not quite sure. Yeah, no, I don't have enough space. So I'm going to use my paper instead. I'll do the sketching under the camera instead. Go ahead. I'm going to do my sketchy bit.
And so we're asking the question about a loop of 18 sticks and what can we do with it? And you don't have to have the sticks. When we're making these shapes, we're going to ask, what are the perimeters and what are the areas? Oh, well, there are 4 different triangles. They're all different shapes, but they're all made with a loop of 18 sticks. And Caroline's doing some sketching while I'm talking.
2, 3, 4. I'm going to go with 5. 5. How many have I got left? 13. Oh, that doesn't sound so good. 2, 3, 4, 5, and then oh, these are going to have to be smaller. Oh, yeah, my angles aren't right here, Tony. 3. I'll change that. Put the 8 there. 1, 2, 3.
I'm
4,
not sure
5,
that the squared
6,
paper
7, 8. So what would be a better solution, do you think? But no, it's going to work. 1, 2, 3, 4, and 5. There's not quite a straight line, but I can get it. So that would be 5, 5, and 8. Whoopsie.
Yes, 5, 5, and 8 works. Now look, the ones on the slide are 8, 8, and 2, 8, 7, and 3, 7, 7, and 4, 6, 8, and 4, and Caroline has just...
I want to do... How about one with 1? Let's see, 1, and then we can go 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not so easy to show that, is it? And then we can go 1, 2, 3, 4, 5, 6, 7. Oh, it doesn't reach.
Long and thin. So
Long thin, but it doesn't reach. They don't join.
what about 1, 7, and 10? That adds up to 18.
Let's see. 1. Okay, let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now 7. 1, 2, 3, 4, 5, 6. Oh, that's even worse.
But Caroline, you've got right angles there, and you don't need to have right angles.
Well, yeah, I know, but
you still can't do it.
no, it won't reach.
Know.
Even if I've got the angles exactly right, it won't reach because I'm 3 lengths short.
So there's a question here: which triples of numbers? So you've got sets of 3 numbers that add up to 18. Which triples will make triangles? And this is something which we're gonna show you. But
well, I got my first one right. My first one worked.
Well, you got them all right, Caroline.
So what would you suggest better than the paper sticks would work? What would you suggest if you're going to draw it would work better?
I really no, Caroline. I really think paper sticks are ideal. I just said if here and now they haven't got paper sticks and they've got a piece of paper, they can be scribbling while they're watching this. They can be trying it by drawing. Drawing's not good for this, really. I think the paper sticks are perfect. So here we are.
Oh, we've got Steve Benton. He was very bad at TGAT. Steve Benton, you've met Steve Benton. He helped us with the Guinness World Record. He's my person that's been with all of them. He's done all the Guinness World Records with me.
So the triangle inequality is what this is called. Technically, it's really a condition that you need for your 3 numbers in order to be able to make a triangle.
That's what I just had. 1, 7, and 10. You
did. And I think you can see from my diagram there why well, I'm asking the question, why is this impossible? Well, they can't stretch. They're never going to meet. 7 and 1 make 8.
Even if they were flat down completely following the line of the 10, they would never meet, even if there was no angle there at all.
And then when you lift them up and try and, you just can't make a triangle. So what do you need? So in order to make a triangle, any 2 edges need together to be longer than the 3rd edge. Now, of course, you could...
Okay, so wait a minute. What about if I had 10? Wait. Let's say if I had 20 and I could have 10 and 5 and 5. They would join together, wouldn't they? We've got 2, 4, 6, 8, 10, and then we could have 5 and 5, and then they would join, but they'd join right in the middle, and they'd then be, so that it has to be longer than that edge. It can't be the same as, because that would just make a straight line, wouldn't it? You just have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we just have 2 straight lines overlapping each other.
Exactly.
So they have to be longer.
Exactly, and that's why it's called an inequality. I mean, together they've got to take any 2, and together they've got to be longer than the 3rd one. And you can put that into a formula, but we're not going to have formulae. We're just talking about the maths here. I don't think, I mean, the formula's very nice because it gives you a general result, but not for today. So we can see why it's impossible for some sets of 3 numbers. But if you've got your triangle, your paper sticks, you can try making triangles and you can see which triples of numbers actually work and which don't. And that's a lovely thing, because the children in a class in school or in your family can discover this result for themselves. And then they are being real, true mathematicians. It doesn't matter that other people have discovered it in the past. For them, it's a first, and they can get all the excitement of discovering it for themselves.
Well,
so that's
I discovered this. I learned it in school, and I learned it as a formula or as a rule, which I never really got it. I actually made the discovery when I was about 45 years old, when I did an exercise like this, and I'm like, oh, so that's why that rule is there. It's not there because to make a rule. It's there because it doesn't work any other way.
Yes.
And it took me actually doing it to understand it.
But I think that's what learning in school should be. It should be a matter of actually doing it for yourself, finding out, ideally very often doing it with a partner, a friend, so you can talk to each other about it and together have that excitement of making the discovery.
Yeah.
Okay, so now we've got the same pictures we saw earlier, and all of these triangles have got a perimeter of 18. If the triangles are different shapes but the same perimeter, do they have to have the same area? The answer is clearly not. You can find that out for yourself. You can explore, and people get, not just children, but adults get confused between perimeter, that's the fence and the edge, length of the edge around something, and the area inside. But they're very different concepts. In fact, people just need the experience of working with both of them in order to...
And it's just learning a word as well. So once you remember the word perimeter, and the perimeter is the fence, and
boundary.
It's the boundary, yeah, and the limit, the perimeter is your limit of your land, that sort of thing. If you own land, or the boundary of your house. It's a matter of remembering that word and distinguishing it from area. But that is a concept that can be a real struggle.
It's surprising because they are so very different. You know,
it's remembering as well. Remembering. So when you don't really understand it, when you don't get it, I've experienced it so many times that a child will just go, oh, is that the perimeter? Oh no, it's that the area. So they know the words, but they haven't, the meaning of those words are not embedded in them. So they know the words, but they're just grasping.
But if they've had an experience of using up some paint to paint the shape, so they're covering the whole area, or tiling it or something, and also getting a piece of string going around the edge. Yeah. Once they understand the concept, it isn't difficult. It's just that somehow or other the teaching is teaching them something to remember when they don't really understand what the concepts really are. Okay, so now what about another puzzle? Starting with 12 sticks and making 3 squares, ideally different.
Okay.
Have you got your 3 squares to show us, Caroline?
Yes, ma'am. I've got one. Whoopsie. Oh, my goodness, dropped it. I've got a yellow square, got a red square, and I've got a green square on the floor. But easier than that, I've got them made out of balloons. I've got a green square, an orange square. That just means it would be a lot easier for me to demonstrate it. And we're doing it. We're going ahead and doing it. Because the question is to make a 3D. Oh, we've got the answer, Toni. Do you know we've got the answer?
No, we haven't got the answer.
See the answer.
Well, okay. All right, we'll get rid of the answer.
So, the way I say it is we're going to make a 3D shape, and usually a 3D shape comes out like this, which is grand. Whoopsie, it's really hard for. I'm just going to look at the balloons and not the screen. There we go. There's a whoopsie, a 3D shape.
You lost your head.
I'm totally lost the plot completely. But the thing is that these have 2 edges, 2 balloon edges together.
That's not allowed. That's not allowed.
We want to make a 3D shape where every edge is unique with 1 balloon edge.
And Caroline,
it's got to be regular.
Please, miss, we've got to have 6 triangular faces.
6?
We do.
6? Are you sure it's 6?
Oh no, that's what the slide says. I think it's 8.
I think it might be 8 too. I hadn't spotted that. So we're going to start with 2 of them. And this is it. You can see Toni and my reaction when we make mistakes. We don't get horrified by it. We just laugh and fix it. We make magnificent mistakes and we learn from them to read the slides more carefully before we publish them.
I've corrected it. But the other thing is, when Caroline does this on this with in one of her shows, she gets kids up on the stage, all grown-ups, and they try and do it, and they try and make that prism shape which she just shows you, that almost every time. Now,
and sometimes they do this. Sometimes they do that, especially when I've only asked for a 3D shape, and this is a perfectly legitimate 3D shape, but this is not a polyhedron, it's not a solid, and it doesn't have any. They're not making triangles with this. You're just making these random 3D shapes, which are very pretty. If you dip that in bubble juice, it's fantastic. It's a wonderful thing to look at. It's got lots of that geometry we were looking at the other day. But in this case, we want all triangles. So how are we going to take this square and add it to this to make triangles? Well, we're missing the horizontal edges. So we can push that down or push it through the center and join them together like so. And hey presto, we have.
That is lovely. I really like that. And what you've got on a piece of paper there is you could have on a piece of paper is something to challenge your other people with, and the steps there are what we call the answer earlier, but they're not really the whole answer. You've still got actually to do it. And when you do,
you just need to make 3 squares.
Yes, 3 squares, and there you have it. And Caroline has just shown you, and there's a picture. And the big question is, well, what is it? It's an octahedron, isn't it?
And a great way to see it is if you just face one way like that, you count 1. Not everybody sees it. Not everybody has that. It's something that comes with practice. Some people kind of comes naturally quite easily, but some people need practice. And on this side, you've got 1, 2, 3, 4 triangles, and then you turn it around completely. The mirror image has the same 4 triangles, and it actually looks the same no matter which way you look at it. So you've got 4 triangles there, 4 triangles there, which is a total of 8
triangles.
And it's called an octahedron because it's got 8 faces. Octahedron. We've got the ancient Greek. Look at you guys, you're learning ancient Greek. This is fantastic.
Yes, and I'm asking you, what do you notice about it? I mean, what else? It's the same shape as Caroline made earlier with the long loop that she made into the octahedron. And yes, it's the same shape. And in fact, the paper triangle one is slightly better insofar as it's more nearly the shape. You can see it's 2 pyramids that are sort of meeting together, 2 square base pyramids that are meeting together, 4 up on the top and 4 down below. Now show us the balloon again, Caroline. And the colors there are very significant. So now Caroline, hold it still. Now Caroline's got the blue square horizontal now, okay, more or less. And in my diagram, you can see the blue square. Well, can you see that that is like a mirror plane? And the octahedron is the same on the top as it is underneath. And if you cut through the blue square, that is a mirror for the top and the bottom of your octahedron. So we say the octahedron has symmetry by reflection in that square. And what about the other squares? In the picture on the slide, you can see the red square. Well, Caroline's is orange. And you can see the square-based pyramid on each side, 2 square-based pyramids on each side of the, yes, up and down. So that's another plane of symmetry. We call it a plane of symmetry or a mirror plane. So there are 3 mirror planes. There's also a green one. And you've got so much geometry there. It's so rich in all the different ideas. It's a fun puzzle, and you can do it all with paper sticks. I like that one.
Yeah,
yes.
that's I love it.
I sort of bet that puzzle because one of Caroline's shows quite a while ago. I can't remember which one, Caroline.
It was it the one in Mute? Well, I do it in all my shows, so you'd have first met it in Johannesburg.
Probably, yes, a while ago.
2009, Toni.
Okay.
September 2009.
Yes, okay. So we've gone through a lot of different puzzles today that you can do with paper sticks, and you can do a lot of maths that follows up on this, or you can just do it for fun of solving the puzzles. And you can make other models too. You've got enough paper sticks. Can I show my
collapsible cube, Toni?
Oh, you can. We've plenty of time.
Cool. So talk about doing different shapes. This is a really good one. So you can see with the octahedron, it's firm. It doesn't. It's rigid. I can only squish that by actually breaking it or breaking the vertices or something. But here is a cube, and in order for the cube to hold its shape, I actually have to hold it. If I let go of any one of the vertices or anything, it just, oh, look at that, it flops down into sticks, just a pile of sticks. But look at this, if I make it into 2D, I can flatten it down to 2D shapes, and look, we can make that shape, we can make a rectangle, we can even make 2 rhombuses, well 4 really, because but flattening 2 down, we can make it into a butterfly.
Yes. Caroline, let's talk about the engineering ideas here.
Yes, please.
Well, no, you're the engineer, not me.
I'm not a structural engineer, I'm an electronic engineer. So the engineering wise, it's why do buildings, if you notice, and even if you can't see them, you will find there are triangles across. You might have square or rectangular windows, but depending on the size of the window, you're going to have triangle supports. Except I'll tell you where there's a place where there's an exception. In Tokyo and in Christchurch in New Zealand, what they've discovered is that actually if they have cuboidal type modules that slip across each other in earthquakes, so because they're smaller size, the cuboids can be quite rigid, and then they're allowed to slip across each other, so that the simple harmonic motion doesn't happen, so they don't collapse. They just, I wouldn't like to be in one skating rink, but in order to keep that shape rigid, this shape will not on its own stay. You've got to either have something on each face that holds it steady, that holds it straight. But even if you have something on each face, it can still, well, it depends.
You could have a brace across, but that would be essentially to form a triangle, so that would be rigid.
The triangles can make it rigid, or you can also have something across the middle, a diagonal brace across the middle. But you can see the difference between a cube made out of squares or rectangles, and shape made out of rectangles, and shape made out of triangles. And I wonder what other shapes will flop and what other shapes will
actually
stay rigid.
It's really the exception that they stay rigid and most will flop. I mean, the main thing is the triangles.
The triangles. So you
it,
find that the shapes that are made up of triangles are the ones that will be rigid, and the other ones will all flop in some way, shape, or form.
And then, so you want your structural strength. And if you look at bridges, long bridges, you'll see that the the structure is built with triangles. You'll see lots of triangles.
You've got the suspension bridges where you've got the vertical bit in the middle, and then you've got all the cables coming down off of it, holding the bridge up, and that's guess what? A triangular shape.
Oh yeah, everything needs to be all the edges to make the struts that make everything strong have got to be making triangular shapes.
But it was interesting that when I discovered about the way that the earthquake, that the anti-earthquake engineering was, that it was these kind of each floor. I don't know if it's each floor or several floors, and they can literally slide across each other.
But then each floor has to be
rigid within itself. Each floor must be rigid in itself, and that's not done just with squares. And
And of course, when we're in school, we want to learn about the different polyhedral shapes. Polyhedra means many. Caroline's been talking about the ancient Greek. Poly means many, and hedra is face. So we're talking about shapes that have many faces. And here you just have what we're looking at with the paper sticks are just the skeletons of these shapes. One thing that you can do is to cut, for example, if you've got this octahedron.
Oh, hold on, Tony. Wait. I just realised. Hold on. We need a technician. Here we go. Right.
If you think about the octahedron, you can make an octahedron and then make some triangles the right size and stick them on the faces, and then you've got something that looks more solid. So you can make Christmas decorations. You can do all sorts of to make your solid shapes.
Make it smaller than that and hang it on the tree and decorate it, as you say. You make decorate
well,
it
you
with all kinds
don't need to make it solid, but you could if you wanted to.
Well, yeah, that's true. You can just do it like make the sticks pretty, or cover it with last year's Christmas paper or something, or whatever wrapping paper you've got, and make it pretty.
So one of the things we do with the teachers is to introduce this idea of paper sticks when teachers are on one of the AIMSSEC courses, AIMSSEC being the organization that I'm involved with in Africa. And they get excited about making these shapes, and then they want to be able to show them off. So maybe they're going to go back to their school, and the children in the class are going to make, we've shown the tetrahedron and the cube, and then there's the octahedron, but there are other shapes that have got more faces, make more sticks, and most of them will be floppy. So what we suggest that they do, and they do very successfully, and when we get photographs to show the pictures, is to hang these shapes up, not by one string. Now you can hang the octahedron up by one string, and there it will sit beautifully, never changing its shape. But you can't do it with a cube, okay? So you can get 4 strings and join them together so that they just suspend the cube, and then under its own weight, the cube will hang down in a lovely cube shape.
And you can make it an engineering project where the young learner has to work out how many strings it will need and where to place them. For example, can it be done with just 2, perhaps? And how would you suspend it if you were only using? So the question would be, what is the minimum amount of strings that would be needed, and where would they have to be, and how would they have to be connected to the ceiling or whatever in order for them to, because if you put them there, it might not work.
And the point is that even if you have a structure where, I mean, this is very floppy, and the string at the corners is very,
yeah, but you can do
loose.
it with two, Tony. You can do it with
but
two.
you can make a woodworking joint, and you can make it hold quite well at those corners. Okay, to in your piece of wood. I mean, your stick can be joined together at really quite a good joint, and it's still weak because any stress or strain on it will break that joint.
Yeah.
I mean, my husband has made lots of furniture and a lot of things from wood, and I've sort of learned from what he's said about all this, that your joint can hold that corner or vertex really firm, and yet even so it's not going to bear any weight, because once you start to put a weight on it, it will for sure it will break.
And that's the reason why you shouldn't lean back on chairs, because you're completely putting the stress in totally the wrong place. And you've always got a lot of chairs, you've got that extra bar going across further down that's not right under the seat. It's like part the way down the chair, because they're the wrong shape. They're just straight down. So that bar's needed to hold the legs from flattening out. And if you lean in the wrong way, the chair is not designed to hold. It'll be under too much stress and it will collapse, and you will go, ouch.
and it's nearly the witching hour of 6 o'clock. But
right.
Before we pass on away, say goodbye until next week.
Before we pass on, dear.
No, I didn't really mean that. Slip of the tongue. The AIMSSEC, I mentioned AIMSSEC. Resources are available. Go to the Aiming High website.
Oh, hold on. I've got to hold on, Tony. They can't see it. Here we go. Put it here. There you go.
There are 4 links for you. And Wholesome Rectangles.
They are all in the description.
So for enjoyment at home and for home and school learning, you've got Wholesome Rectangles, which is well, the word rectangles is in the title. It's really all about number. Lots of number puzzles in there. The Tets and Octs puzzle we've worked through this afternoon. We've talked about meter measures, making that meter stick and doing lots of measurements. And there are 8 videos on the AIMSSEC YouTube site, all about paper sticks and different things that you can do with paper sticks.
And that is called MathsToys. The AIMSSEC YouTube channel is called MathsToys.
Well, the reason Caroline and I called it MathsToys was because we wanted people to enjoy their maths, so hence the toys idea, and that it's a good way to playing with maths is a good way to learn maths.
Yep.
So, and that's a good note on which to finish.
Yeah, that's a brilliant note on which to finish. To enjoy maths is to learn maths. Yes. And so we'll see you next week at 5 o'clock London time with Happy Maths Hour. Tony's the one that does the bulk of the work on this. I'm going
to have to stop you saying that, Caroline.
Okay. Well, the thing is that I never know what we're doing until Sunday. We don't know what we're doing until Sunday, so we can't tell you what we're doing next week. But we look forward to doing it, whatever it is, and please join us. And we'll see you next week at 5 o'clock London time. Same place, same time, same place. See you next week.